Hey everybody, in this video, we're going to talk about concavity and inflection points. Let's learn about concavity and inflection points with an example. Suppose we have a function like f of x that's shown here. The section of the graph that's highlighted is concave up. What this means is that tangent lines for this section of the graph are below the curve. Also, if we look at the slopes of the tangent lines going from left to right, we can see that the slopes are increasing. Now let's consider the highlighted portion of the graph on the left. This section of the graph is concave down. Note that the tangent lines in this section are above the curve. Also, if we move from left to right, the slopes of the tangent lines are decreasing. Now there's a point on the graph where the function changes concavity. In other words, there's a point where the function changes from concave down to concave up. This point is called an inflection point. The blue graph shown here is the first derivative of the function. Note that in this case, the inflection point corresponds to a local minimum on the first derivative graph. In other words, this is where the first derivative changes from decreasing to increasing. And that's where the slopes of tangent lines on f of x change from decreasing to increasing. The green function shown here is the second derivative of f of x. Note that the inflection point of f of x corresponds to the x value where the second derivative changes signs. Let's take a look at all of this from a few more angles. Here I've highlighted the part of f of x that's concave down. Note that this corresponds to where the first derivative is decreasing. This also corresponds to where the second derivative is negative. And here I've highlighted the portion of f of x that's concave up. Note that this corresponds to where the first derivative is increasing. And this also corresponds to where the second derivative is positive. Let's do some example problems. Example 1. Find all inflection points and intervals of concavity for f of x equals x cubed minus 9x squared plus 27x minus 26. Let's start by finding the first derivative. F prime of x equals 3x squared minus 18x plus 27. Then we'll find the second derivative, which is 6x minus 18. Then we'll set that second derivative equal to 0 and solve for x. And when we do that, we get x equals 3. Now let's place x equals 3 on a number line and chart the signs for f double prime of x. Any number we plug in to the left of x equals 3 would produce a negative second derivative, and any number we plug into the right would produce a positive second derivative. Since f double prime of x changes signs at x equals 3, that means that f of x has an inflection point at x equals 3. We can also say that f of x is concave down on the interval negative infinity to 3, because f double prime of x is negative on this interval. And finally, we can also conclude that f of x is concave up on the interval 3 to infinity because f double prime of x is positive on that interval. And here's a graph of f of x, where we can see the inflection point at 3f of 3. Let's do another example. Suppose f double prime of x is shown below. Determine where f of x has inflection points. Here we just need to determine where the second derivative changes signs, and that occurs at x equals negative 2. So we can conclude that f of x has an inflection point at x equals negative 2 because f double prime of x changes signs at this x value. And don't be fooled, f of x does not have an inflection point at x equals 1. Even though f double prime of x equals 0 at x equals 1, f double prime of x does not change signs at this x value, so there's no inflection point at x equals 1 on the graph of f of x. Here's the graph of f of x, which will help us see this visually. At x equals negative 2, we can see that there's an inflection point. This is where f of x changes from concave down to concave up. Let's do one more example. Suppose we start with a graph of f prime of x. Where does f of x have inflection points? So in this case, since we're given the graph of f prime of x, we need to determine where the graph changes from increasing to decreasing, and vice versa. In other words, we need to find the local maxima and minima on the f prime graph. So we can conclude that f of x has inflection points at x equals negative 1 and x equals 1. because that's where the first derivative changes from increasing to decreasing, and vice versa. And here I've overlaid a graph of f of x in green so we can see the inflection points at x equals -1 and x equals 1. Here's a helpful chart to help you sort out the details between f, f prime, and f double prime. When f of x is increasing, f prime is positive. When f of x is decreasing, f prime is negative. When f of x is concave up, f prime is increasing, and f double prime of x is positive. And when f of x is concave down, f prime of x is decreasing, and f double prime is negative. F of x has inflection points where the second derivative changes signs, which is also where the first derivative changes from increasing to decreasing, or vice versa. And that's how you rock calculus!